Hello, and welcome to the next video in my series on finite mathematics. Now, a few things before we get started. Number one, if you're watching this video because you're having problems in a class right now, I want you to stay positive and keep your chin up. If you're watching this video, it means you've come pretty far in your education up to this point, and you may just be in a temporary rough patch. Now, I know with the right amount of hard work, patience, and perseverance, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up, so that does encourage me to keep making them. On the other hand, if you think there are things I can do better, please leave a constructive comment below, and I will try to incorporate that into my future videos. And finally, just keep in mind that these videos are geared towards individuals who are relatively new to finite math, so the examples I will be using will be gone over in a very deliberate, a very slow method. So I want you to understand what's going on and why it's going on. So all that being said, let's go ahead and get started. So this is our next video in a series of videos on Markov chains. In the previous videos, we've talked about the very basics of Markov chains, all the way through one-step transition, two-step transitions, and in the last video we talked about long-run transitions. And in this one, we're going to actually talk about how to calculate the long-run probabilities exactly, using matrix operations, systems of equations, and things of that nature. So, I just need to tell you up front, I am going to assume you have a basic understanding of what Markov chains are. Either of you watched some of my previous videos or you've gotten enough out of class to understand what they are at their most basic level. I'm also going to assume you can do basic matrix multiplication and solve basic systems of equations. I cannot go back and go over that in every video, because that would be even longer than they already are. So I'm going to assume you have some basic understanding of those things. Now you might want to have a pencil and paper handy for this video, because matrix operations are a lot easier to understand if you're actually doing them, in class or along with me. So if you want to pause it and grab a piece of paper and pencil, feel free to do so, because it can help you internalize what we're doing. So let's go ahead and dive right into the meat of the video. So in the previous video we talked about long-run transitions or long-run probabilities, and they had this basic general form. We had some sort of initial state vector on the left-hand side. In the middle we had our transition matrix, and we took that transition matrix and raised it to a power, to an exponent, that represented however many steps into the future we were interested in. So in our example, we were talking about auto insurance risk. And every time one of our customers renews a policy based on their driving record, we put them in a high-risk group or a low-risk group. A year from then, we do the same thing. A year after that, the same thing. A year after that, the same thing, etc. So if we're interested in the probabilities of a driver being in high risk or low risk, say 20 years into the future, M would be 20 in this case. So we're just taking our transition matrix and running it through many, many years in this case, or steps or trials or whatever the problem asks you to do. So this is just the general form. So when we did that in our problem, this is what happened. We raised the exponent to 2, and then to 5, and then to 10, and then to 20, and then all the way up to 25. When we did that, something quite odd happened. The long-run probabilities stopped changing. So our transition matrix to the 20th power gave us the same result as our transition matrix raised to the 25th power. And if we did to the 50th power, it would still be the same. It just stopped changing the more we went in to the future. Our probabilities stabilized, and we call those the steady state probabilities. Now, the method we use here is kind of, roughing it. We just put this in a calculator and change the exponent over and over and over again until the probability stopped changing. In this video, we're going to talk about how to actually solve for them exactly using matrix operations and things of that nature. So let's go ahead and start doing that. So just a general idea before we get into that actually. So eventually continuing to multiply our answer by the transition matrix again and again and again has no effect on the outcome. So 25 years into the future is the same as 50 years into the future with respect to our auto insurance. And we had this general form here. It's just simple sort of an algebraic expression where we're saying that V, our initial state vector, times P, our transition matrix, gives us back V. So initial state vector times transition matrix gives us back our initial state vector. Well, that sounds a whole lot like multiplying our initial state vector by 1, since we get the V back at the end, right? That'll be important here in a minute. So multiplying P by the transition matrix has no effect. It just returns V again. So in our auto insurance, we said that the way to interpret this is that drivers, way into the future, they will continue to move between high risk and low risk from year to year. But what's going to happen is the numbers going from one to the other and back and forth will become the same. Therefore, the proportions in each state will remain the same. So if you think about this, if I have two groups of people, group A has 75 people, group B has 25 people, if one person leaves A and goes to B, one person leaves B and goes to A, well, the proportion's still the same. It's still 75-25. And that's kind of what happens into the future with these long-run probabilities. So let's look at this equation and talk about it because it's very important to actually solving these for the exact probabilities. So here's our starting point. V, our initial state vector, times P, our transition matrix, gives us V in return. So another way of thinking about that is our initial state vector, which in this case, we don't know. We're trying to solve for it. We're trying to find out exactly what it is. Now, in the previous slide, or a couple slides ago, we kind of forced the issue by raising our transition matrix to a very high power. But that's not really how you solve these. That was sort of the brute force method. So here we're saying, well, we don't know our steady state vector. So we're going to just call it x and y, and that's what we're going to try to solve for. And when we multiply that by our transition matrix, we're going to get our vector in return. So some matrix on the left multiplied by our transition matrix in the middle will result in getting our probabilities and our vector back. So in this case, our unknown steady state vector is V. That's what we're solving for in this video. So how can we do that? Let's look at this equation again. Now we're going to use some simple algebra skills to actually get to the point where we can figure this out. So just follow along and you'll see, if you remember algebra, it should be pretty clear. So what can I do with this expression? Well, I'm solving for V, the steady state vector. So I can subtract V from both sides, and it looks like this. So I subtract V from the right and from the left, and we have V times P minus V equals 0. So that should be pretty clear up to this point. Now we can do some factoring. We can factor out V on the left side because it's sort of common to both terms there. So it looks like this. V parentheses P minus 1 equals 0. And that's just simple factoring. There's nothing complicated about that. Now the next step, you kind of have to know a little bit about matrices. Now in matrix multiplication, an identity matrix, which we denote with the capital letter I, is sort of the equivalent of 1. So look, if I multiply V times an identity matrix, I would get V back. So another way to write this is V parentheses P minus I equals 0. So again, you have to know a little bit about how matrices work to know that in this case 1 and I are functionally the same. Okay, just for the purposes of this, they are functionally the same in terms of multiplying. So now we have this nice equation down here, V times P minus I equals 0. And we actually have all that information except for V, which is what we're trying to find. So here's our equation we're going to use. Now we know that V is our unknown. That is a matrix or a vector of X and Y. That's going to be our steady state matrix when we solve for it. So we know what P is. That's our transition matrix, which we've always had in our problem. And then I is the identity matrix that corresponds with P. So of course P there is a 2 by 2 matrix, so its identity matrix is also a 2 by 2. So we have all the information we need to actually insert into our problem. Now also remember that X plus Y has to equal 1. So whatever probabilities we have in our vector have to add up to 1. They can be 0.5 and 0.5, or 0.3 and 0.7, or 0.9 and 0.1. Doesn't make a difference. They just have to add up to 1. And that's important because we have to factor that in to the way in which we solve this problem. Okay, now this is where you might need your pencil and paper. So if you need to get it, pause the video, and that way you can follow right along. Okay, so we have V times P minus I equals 0. So we'll substitute what we have into that equation. Now P is our transition matrix. That's there sort of in the left-hand side in the bracket. And we have the identity matrix sort of on the right-hand side inside the bracket. Of course, X and Y is what we're solving for. We don't know that yet. And of course, all that equals 0. So remember, when we subtract matrices, of course, they have to be the same dimensions. So these are both 2 by 2 inside the brackets. And it's simple subtraction with corresponding elements. So when we do that, we have 0.6 minus 1, because they're both in the top left of those matrices. So 0.6 minus 1 is negative 0.4. Then we have 0.4 minus 0. Those are both in the top right of those two matrices, and so on and so forth. So then we have the bottom, we have 0.15 minus 0, and then 0.85 minus 1. And that's just simple subtraction of corresponding elements in those two matrices. That's all we did there. So now we have a new matrix inside the brackets. We still have our probability vector on the left-hand side, and that's all set equal to 0. Now we're going to do some basic matrix multiplication. And remember, that's just row times column. So we're going to take our vector row, the X and Y, and then multiply that with each column in our matrix on the right-hand side. And then we come out with this. So X times negative 0.4 is negative 0.4x, plus Y times 0.15 is 0.15y. Again, row times column, and then we go to the next one, row times the next column. Okay, simple matrix multiplication. And then we end up with these two equations. Now, if you look at them just off the top of your head here, you should think that, well, those look very similar. And that's because they are. If we multiply the entire top equation by negative 1, we end up with the same equation. So those two equations are identical. And of course, when we're dealing with systems of equations, we don't have identical equations because, you can think of in graphical terms, they're actually the same line on a graph. So they're the same thing. We only need one. So we can actually collapse that into one equation. We don't need the second one in the next step. Okay, so we know a couple things at this point. We know that whatever we get for x and whatever we find for y have to add up to 1. So we have an equation there. X plus y must equal 1. Then in the previous slide, we found another equation using our matrix operations. And that was 0.4x minus 0.15y equals 0. So those are our two equations we're going to work with in finding this problem. Now I will say here, when you have two equations like this with only two variables, it's much easier to solve it just by solving a system of equations, which I actually did in the previous video. But I'm actually going to do the matrix method so you can see actually how it's done using matrix operations. So I thought a simple example would be a good starting point. So here's where we're starting. First thing we're going to do is we're going to put this into matrix form. So here's how we did that. Now we're looking at the coefficients with the variables at the top. So x, the coefficient is 1 up there. For y, the coefficient is 1. And then we have the 1 right of the equal sign. So in the top row of our matrix, we have 1, 1, 1. On the bottom row, I just converted these to hundredths. So 0.4 is 40 over 100. 0.15 is 15 over 100. And I chose 100 because the 0.15 works a lot better if we're doing it in hundredths. So I just converted decimals into fractions. That's all I did. It's nothing more complicated than that. Okay, now remember, our goal is to use the Gaussian method, you've probably heard that in your class, to make our matrix here in the middle in row echelon form. I'm sure you've probably heard of that. But basically our goal is to get this matrix in the middle, the big one, to look like the small one up there in the top right. And we're going to do that using our matrix operations. So here's the way I'm going to approach this. Now this is the method I use when I'm solving these, and I use with my students I work with. So you can choose to do this, or you can use whatever method that's taught in your class. But here's the way I interpret that expression on the right hand side. I have negative 40 over 100, and I'm going to multiply that by the first row. So negative 40 over 100 times row 1. So basically I would have negative 40 over 100 across the entire top row. But we're not doing that, writing it down. We're doing it in our head. So negative 40 over 100 times row 1. And then we're going to add that to row 2. And then put the answer in row 2. So let's just do the example here, how we're going to do this. So let's look at the one in the top left. So negative 40 over 100 times 1 plus 40 over 100. So what's negative 40 over 100 plus 40 over 100? Well, that's 0. Okay, 0. Now let's do another one. I'll actually put the answer down here. Let's look at the second one in the second column up there. So negative 40 over 100 times 1, that's negative 40 over 100, plus negative 15 over 100. Well, that equals negative 55 over 100. And that's there at the bottom. And then finally we have negative 40 over 100 times 1 up there in the upper right, plus 0 is negative 40 over 100. And again, that's just a basic Gaussian elimination when we're doing row echelon form. So again, I'm assuming you kind of know how that works, that you've picked up enough of it in your class so that this actually makes sense. Okay, let's go ahead and continue. So here's where we left off. Now on the left-hand side, that's kind of where I put simple operations I do that really don't affect the overall, numbers in the actual matrix. In the previous slide, then 55 over 100 and 40 over 100 were both negative. Now, I don't like having negative signs if I don't need them, because it's just one more thing to get in the way, keep track of, and go wrong. So I just multiply the entire bottom row by -1. And that essentially gets rid of the negative signs. I don't have to worry about any more negative signs in the bottom row. Makes the matrix nice and clean to work with. And again, they just don't get in the way. Because many a times, oh goodness, how many times have I seen a student that forgot to carry a negative sign or had a mark on the paper that they interpreted as a negative sign and actually factored that random mark into the problem. So the idea in my philosophy is to keep that matrix as simple as possible. The fewer moving parts there are, the few parts there are to go wrong. Okay, so that's my little speech on negative signs. Now, remember, our goal now is to get the second column to be in row echelon form. If you look at our first column, that's perfect. We have 1 and then 0. But now we need to have 1 where the 55 over 100 is, and 0 where the 1 is above it. So how are we going to do that? What I'm going to do is I'm going to take the second row and I'm going to multiply it by 100 over 55. Now think about that. What's that going to do? Well, if I take 0 times 100 over 55, that's 0 still. Doesn't change that. 55 over 100 multiplied by 100 over 55 is 1. It's the reciprocal. So by multiplying 55 over 100 by its reciprocal, I get the 1 I need in that spot. Now, of course, we have to do the same thing to the 40 over 100. So 40 over 100 multiplied by 100 over 55 gives us 40 over 55. So here's where we are. The top row is still all 1s. The bottom row we have our 0 and 1 like we need. So really the only other thing we have to do is get rid of the 1 there in the top right on the sort of left-hand side of our matrix box. Now, technically speaking, you don't even have to do this step. When you have two variables, and actually right now we've already found one, whether you know it or not, we really don't have to do the next step, but we're going to do it anyway. So, in the 1 spot, there in the second column at the top, we need to get that to 0. So here's how we're going to do that. -1 times row 2, we're going to add up to row 1, and then put our answer into row 1. So think about that. I have -1 times 0, which is 0. Add upward. 0 plus 1 is 1. Now I take -1 times 1, then add upward. -1 plus 1 is 0. So that's going to get us our 0 in the top right of the sort of the left-hand side of that matrix. Then -1 times 40 over 55, well, that's -40 over 55 plus 1. So -40 over 55 plus 1 is 15 over 55. And there we go. So just by doing some simple matrix simplification using the Gaussian method, we get our matrix in row echelon form. And actually, believe it or not, on that right-hand side, that's pretty much our answer. We just have to simplify it, and then we've got it. So again, if you're not that steady or that confident in your matrix skills, you know, this is a good time to pause the video, look at exactly what I did so you understand each step. There are a lot of intermediary steps when you're doing this sort of thing with matrices. And if I wrote out every single intermediary step, it would be a mess. So some of these things you just have to do in your head temporarily so it doesn't become, you know, a crazy mess on your paper or on this slide. Okay? So that takes us to the matrix on the lower right. So those are where we ended in our last slide. Now if we simplify those fractions, okay, because we can divide the top and bottom all by 5, So 15 divided by 5 is 3, 55 divided by 5 is 11. So our top fraction is 3/11. Our bottom fraction is 8/11. And there are our values for x and y. Because when we look at that matrix on the left-hand side at the bottom, we're saying 1x equals 3/11, or x equals 3/11. On the bottom, we're saying 1y equals 8/11, or y equals 8/11. So there they are, there in the top right of the slide. So this is actually our steady state vector. So the probability of being in state 1 in the long run is 3/11. The probability of being in state 2 in the long run is 8/11. And that's actually our answer. So let's make some sense out of this before we go. So remember, this is our initial little equation we were working with. V times P equals V. So V is our steady state vector, P is our transition matrix, and we multiply those together, we get V in return. So remember, this is why we set it up when we didn't know what the steady state vector was. But now we can. So we found our answer. Our steady state vector is 3/11 for x and 8/11 for y. So if we take a vector or a matrix that's 3/11 and 8/11, we multiply that by our transition matrix, guess what we get for an answer? We get our steady state vector back. You can actually do this in your graphing calculator, and you'll see that the vector of 3/11 and 8/11 multiplied by our transition matrix gives us our probabilities back, gives us our vector back. It's like multiplying it by 1. And that just shows you, no matter how many times we multiply that by our transition matrix, we're always going to get 3/11 and 8/11 back. So this is the actual exact way of figuring out our steady state matrix. Okay, now I just wanted to point out on that previous slide, if you remember, actually I think I'll go back. We have 3/11 and 8/11. Now if you do the division in your calculator, you will see that 3/11 is 0.27272. 8/11 is 0.72727. Those are the exact numbers we found when we took our matrix and multiplied it many times in the future just using our graphing calculator. We changed the exponent to 10, 20, and 25. We got these decimal numbers that were 0.27272 and 0.72727. Well, guess what? Those two decimals are approximations of 3/11 and 8/11. So you can see those are the same answers, but this is the exact way of doing it. Okay, so that wraps up our video on how to calculate simple steady state probabilities or steady state vectors, steady state matrices, using the matrix method to actually find the exact values. You can use the brute force method, and again, that's just by raising the exponent of the transition matrix to some insanely high number, and you will get, usually you will get the steady state matrix in decimal form on your calculator. But that's not the way of finding it out exactly. To find the exact numbers, you have to do the matrix operations that we did in this video. Okay? So, just a few things and then we are done. Number one, just remember, if you're having problems in your class right now with respect to Markov chains or anything else, I want you to stay positive, realize that you are very smart and you're very talented. And this may just be a temporary rough spot and you can get through it. Again, if you're watching this, it means you care about learning. So I have faith in you, and so should you. Number two, just remember to follow me here on YouTube and or on Twitter so you get new videos when I upload them. If you like this video, give it a thumbs up, add it to a playlist or something like that. Otherwise, leave a constructive comment and I'll try to make it better in the future. So, all that being said, I want to thank you very much for watching. I wish you the very best of luck in your studies, and I look forward to seeing you again next time.